To investigate confidence intervals for proportions, we're going to look at a big container of red and white beads that I have in the classroom. The first thing I'm going to do is use my little bead paddle and do a random sample of 20 beads. And notice in this 20 beads I got 6 of them that were red, so I have a sample proportion of 0.3. Now we talked about before that the sample proportion is my single best guess for the population proportion if I don't know what the population proportion is. And I actually don't know exactly what the population proportion of these red beads is. So I'm going to use this to estimate. So we have to remember some things that we remember about the sampling distribution of p hat. So we remember a few things. We remember that if these are a bunch of p hats, that the mean of all the p hats is just p, the population proportion. So I would expect that to be in the center, and that the standard deviation of all of my p hats is the square root of pq over n, and that it's approximately normal if np and nq are both greater than or equal to 10. The problem is I don't know p here. I only know p hat. So the best thing I can do is to say, well, I don't know what p is, so my best guess for p is my p hat. So I'll put p hat here in the middle for the center. And I will then make a distribution with a standard deviation of the square root of p hat q hat over n, and I'll check my normal condition by using p hat and q hat also, because that's all I have. I don't have anything else to use. So first of all, when I'm thinking of this p hat q hat over 10 thing, I'm thinking, if I do 0.3 times 20, that's only 6. So that's not going to actually satisfy the normal condition. So I'm going to probably need to take a bigger sample, because if this had been about 50%, I would have been okay taking a sample of 20 for 20 times 0.5 is 10, but not with this. So my preliminary sample tells me I'm going to have a bigger sample size. So let's kind of delve into this whole idea of the sampling, of using a confidence interval to estimate a population proportion. This is officially called a one-sample z interval for a population proportion, and this is what it's going to look like. I'm going to take my sample statistic here. Actually, let me write this a little bit differently. Let me just remind you that we do a point estimate. Oops, that's not spelled correctly. We do a point estimate plus or minus a margin of error. The margin of error consists of two parts: the number of standard deviations that I'm going to add to my point estimate and how big those standard deviations are. So my point estimate here is p hat. That's my sample proportion. That's my single best guess for the population proportion, because I don't know what the population proportion is. If I knew, I wouldn't have to estimate it. Then plus or minus, the z critical value is the number of standard deviations I need to add to get the appropriate level of confidence that I desire. This is going to be multiplied times the standard deviation of the statistic, only we're going to call it the standard error of the statistic. And the reason we use that term is because it's slightly different from the standard deviation of the statistic. Recall the standard deviation of p hat, in other words, how much the p hats vary from each other within a sampling distribution, is based on the population proportion. So this is unknown though. So from the population proportion, which is unknown. So I call this the standard error of p hat. The standard error, if you go down to this next definition here, is the standard deviation of the statistic p hat that is estimated from the data. Okay, so if I get some data and I calculate a standard deviation, like my sample of beads, that is where the standard deviation comes from. Now, the critical value measures how many standard errors we need to get the desired level of confidence. So all of this together, these two pieces together, form the margin of error. Now, how do we get the critical value? That's the first piece. We pretty much know how to do these other two things. We've done those before. But how do you get this critical value? So the critical value is a particular z-score that cuts off a confidence level that I want to get. So, for example, if I want to do a 95% confidence interval, then I want this area in between these two cutoff points to be 95%. So this upper cutoff point is the z-critical value. Now the lower cutoff point would be the opposite of the z-critical value. So this is based on a normal model, a standard normal model where mean is 1 and standard deviation is 0. So these are all of our z-scores in a normal model. And so when I want 95% confidence, this is what I'm looking at. Now, to find what this is, I need to do inverse normal. But if you recall, inverse normal gives you the z-score that is above a certain level of a certain area under the curve. So if this is 0.95, this is going to be 0.025 and 0.025 because there's 5% left over and I have to split it between the two tails. So this is going to be 0.95 plus 0.025 or 0.975. So to find the confidence or find the z critical value for a 95% confidence level, I would do inverse norm on my calculator 0.975. So let's go ahead and do that. So you're going to menu, statistics, distributions, and 3, inverse normal. I put in the area under the curve, 0.975, and push OK. And that's 1.959. Now remember that when in the past we've said, oh, plus or minus 2 standard deviations surrounds that middle 95% of the data. And it's pretty close to plus or minus 2, but that's more of a rule of thumb. The exact value is 1 point, and we usually use 1.96. So this is equal to 1.96. The z critical value now that we'll use to cut off a 95% confidence interval is 1.96. 2 is pretty close, but that's just an estimation. Now to do 0.9, let's do another one here with a picture. So if I want to do a 90% confidence interval, this would be 90% in here. And this then would be 5%, so this would be 0.05 and 0.05. So this value here that's below my z-critical value would be 0.05 plus 0.90 or 0.95. So I would do inverse norm of 0.95. And that turns out to be 1.644 something that rounds up to 1.645. And usually we use 3 digits for this one because it's kind of in between. 1.65 is a little too high, 1.64 is a little too low, so we do it like this. Then 98%. Okay, well you're going to have 98% in the middle with 1% here and 1% here. So what's going to go in there is 99%. The middle 98% plus the lower tail. So this would be 0.99. This turns out to be 2.33. And then for 99%, there's going to be a 0.5% on either trail. So this is going to be 0.995, which ends up being about 2.58. So the number, so this is why higher level of confidences give us wider intervals, because this critical value gets bigger with each level of confidence. Another thing we have to be able to do before we start making our confidence intervals is know how to check the conditions for making the confidence intervals. We already saw one that was violated earlier when I had only a sample of size 20. It would not have created an accurate confidence interval because the sample size was too small for that proportion. So what are the 3 big ideas here? Condition number 1 is the random condition. We either have p hat comes from a simple random sample or from a randomized experiment. Now technically it does need to come from a simple random sample, but most of the time we just say random sample. It's kind of beyond the scope of this course to differentiate between different types of random samples. So it's okay to just say random. So I'm just going to actually cross this out and say a random sample. So I'm going to kind of erase. Sorry, I know you guys are writing notes and I'm messing it all up. From a p hat comes from a random sample or a randomized experiment. Oops, I put that on the wrong side, didn't I? A randomized experiment. Okay. Now, what's the effect of violating the condition? Probability rules won't apply unless we have random events. Okay, so that would be the problem. If we violate that, we can't use all of our probability rules that we're using for the normal model. So this particular condition affects the p hat. Where does the p hat come from? The second condition has to do with the standard deviation of p hat, and this is the 10% condition. And this says if, and only if you are sampling without replacement, now I want to emphasize this condition only applies if you're sampling out without replacement. Otherwise, you don't have to check this. If you're sampling without replacement, the sample size n has to be less than 10% of the population size, which we symbolize with a big N. If this is violated, the standard error is not accurate because it's based on that condition. It turns out that the confidence intervals end up being too wide. Sorry, I'm writing really, really sloppily, so let me try this again. Confidence intervals are too wide. Okay, the last condition, the third condition, has to do with our ability to use our z critical value. We can only use our z critical value if this p hat, the distribution of p hat, it forms a normal model. So this is our normal large enough condition. In other words, is our sample size, is the combination NP or NQ large enough to use a normal model? So we say NP hat greater than or equal to 10 and n times 1 minus p hat greater than or equal to 10. Of course, this we often call that Q hat, but technically it looks like that on the AP formula sheet. Actually, I don't think that's on the AP formula sheet, but anyway, that's the typical way we write it. If the distribution is not approximately normal, then we can't use the normal model. If not normal, we can't use z critical values to form the interval. Okay, so each one of these conditions applies to a part of the formula. So now we've learned a little bit about a confidence interval, about the formula for a confidence interval, and how to find some certain things. In our next video, we'll go back to our beads example, and we're going to make a confidence interval and write about it.